Okay. So this honors calc is just more practice with optimization problems. So for those of you who like to see a few more sample problems before you work into a homework set, that's what this is. So FYI, in case you have not found it, you can pause me in a minute. There's a document on Schoology which says, I think like 3.7 additional practice lecture guided notes or something like that. You'll figure it out. And there are 4 problems on it. If you open it up, and those are the 4 problems I'm going to solve right here so you can see me do it. And the other thing that might be useful there on that document is then I posted which of the homework problems they are most similar to. So I covered, there's 9 homework problems on this worksheet, and I covered, I think, 8 of the 9 between these 4 that I'm going to do now. I didn't want to push, I want to make you think about the process a little bit, so I'm not going to do every single one. But you should, based on what I'm doing now, feel pretty confident with 7 or 8 of those 9 problems. So the first one is kind of a review because we've really seen it already, and then the next 3 are just a little bit different from things that we worked with last week. So let's start with the review one. So the review one says 2 positive numbers whose sum is 110, where we want to find them, and whose product is a maximum. So this is problem number 1 on the guided notes. So what am I given? I know that I have 2 numbers, and their sum is going to be equal to 110, and I want to find the maximum product. Well, I don't want to find the maximum product, I want to find the numbers, but they're going to have a maximum product. So that's what I know. What do I want to find? I want to find those 2 numbers. That's what I'm after. Okay. So we have to think, what's my primary equation? What's my secondary equation? A primary equation is always the thing you want to maximize or minimize. So in this case, they're telling me it's going to have a maximum product. So the product of the 2 numbers is, I'm going to call my numbers x and y. So it's x times y. That's the thing I want to maximize. My secondary equation, since I have 2 unknowns in that first equation, my secondary equation is going to relate the variables to each other. So I know that the sum of the 2 numbers is 110. So 110 is equal to x plus y. So essentially, I'm doing the same thing I did last week. I'm going to start with that secondary equation, solve for one of the unknowns in it to get this primary equation in terms of only one of the independent variables, and then I'll do my calculus. It is usually helpful to think about your feasible domain. In this case, if we want the max product, of course, it's going to be positive. So we're going to have 2 positive numbers, and multiplying by 0 will give you 0. So if we go to, so it could be like 110 and 0, for instance. So it could be 109 and 1. So all the way up to 109. Not include, we could say to 110 because it doesn't include 0 or 110. Whatever. Point is, just think of like kind of a reasonable range. Okay. So when I'm solving these problems, here's again, this is the thing I want to maximize or minimize. In this case, I want to maximize it. And my secondary equation is 110 is equal to x plus y. So I'm going to solve for one of my unknowns. I'm just going to try to do what I have in my notes. So I solve for y. Y is equal to 110 minus x. And so I plug that in to this equation. So P is equal to x times y, which is 110 minus x. So P is equal to 110x minus x squared. So just algebra, getting the function that I want to maximize or minimize in terms of one variable only. So that's what I have done. Then you want to find the critical points for this function, because those are likely where we're going to have maximum or minimum. So I'm going to take the derivative. So the derivative is equal to 110 minus 2x. And I want to find where is that 0. So 110 minus 2x is equal to 0. If I solve this, I have 110 is equal to 2x. So x is equal to 55. Now, I need to use either the first derivative test or the second derivative test to figure out or confirm, is this where a maximum value is hit. This is a nice place to use a second derivative because the second derivative is a constant. The second derivative of this function is equal to -2. So because I have a negative second derivative at my critical point, because it's -2 everywhere, so it's defined at 55 and it's negative, that means we have a maximum. So we have a maximum by the second derivative test. So if x is equal to 55, then we go solve for y, and y will end up being 55 as well. And so those are my two numbers that give me a maximum product and add up to 110. This, again, was a lot like some of the problems you did last week for me. So let's move into the second problem on those guided notes, which is a little bit different. Let me find my eraser. Okay. So the second problem had a square that was 24 inches on each side. Okay, so you had a square, and that's supposed to look like a square, that's 24 inches on each side. And what you're going to do is cut squares out of the corner of each side so that you can fold it up and make a box. So, for instance, this is not a square, but I did this with a piece of paper just so you can picture it. So this was an 8.5 by 11, just a regular piece of paper. So it didn't start as a square, but same idea. I cut squares out of each corner of this piece of paper so that if I fold the corners up, or the sides up, I will make a box. This is how you can make boxes, right? So if you have sheets of cardboard and you're in the business of making boxes, this is a way to do it. So if I fold these up, like pizza boxes, I mean, this way. I don't know how well you can see on the camera, but I have made a box, right? It's clearly I didn't tape it together. I just folded it, but you get the idea. Okay, so that's what this problem is about. So you have one sheet of cardboard that's 24 inch size, and you're going to cut squares from the corners. So we're given, I should say, this is my given. It helps me to picture it. So I have a sheet that's 24 inches on each side. I'm going to cut squares from the corners. And I want to, in order to get my maximum volume. So if you think about it, like the more you cut you lose a lot more, right, on the length or width of your box, but then you gain a lot more on the height. So it's sort of like, what's the best way to do that? And so we want to find the dimensions you should cut out. Okay, so if I have this sheet that is 24 inches, and if I picture cutting things out, right, to fold it up and make a box, I'm going to redraw this. This is how I picture it. So I'm going to cut out squares of side x, right, and it has to be the same size square. I know I'm standing in front of what I'm talking about, sorry. So let me draw it. Okay, it has to be the same size square on each of the four corners. And because they're squares, I'm going to call it x, so x by x. And so if I know I started with a 24 sheet of cardboard, this would be 24 minus 2 times x, right, on each side. So my primary equation. My primary equation is the thing I want to maximize or minimize. It's the volume of the box. So my primary equation is equal to the volume of my box. So volume is equal to length times width, which would, well, because I didn't draw this very well, sorry. This thing, so whatever the width of the box ends up being, is 24 minus 2x. And same deal over here, 24 minus 2x. So the length, because it's all a square, of the box is 24 minus 2x. The width of the box is 24 minus 2x. I'll just write it again. Of course, you could write square. That's the same thing. The height of the box ends up just being x, right? When you fold those sides up, like I was showing you with my piece of paper, that gives it a height of x. Now, let's look at this equation. There's only one unknown in it, x, right? I can simplify. I'm going to clean it up a little bit. But secondary equation is not needed. So that's what's different about this problem. We haven't done one of, I shouldn't say x because we're talking about variable. I mean, like, let's say n. I was trying to draw like a cross here. We don't need it. It's not applicable. So x was probably a bad symbol for that since that was also my variable. So if we take a look at this, because my primary equation only has x in it, I don't need to substitute or do anything with it, right, to get rid of a y or an h or anything like that. And so what I'm going to do is just clean this equation up and find its critical points and solve. If we're thinking about a reasonable domain, feasible domain, well, clearly it's going to have to be a positive number we cut out of the box because you can't do it otherwise. And you wouldn't cut more than 12, like if you cut 12 inches, right, times 2, you're left with nothing. So it's got to be something less than 12. Okay, so what I'm going to do is take that primary equation and clean it up. I'm just going to distribute this out. So this becomes V is equal to, I'll pull this x out in front, x times 576 minus 96x plus 4x squared. And you distribute this all out. So V is equal to 576. Well, let's put the x cubed in the front. Sorry, just because I like that. 4x cubed minus 96x squared plus 576x. Okay, so there's my equation for volume. Just want to clean it up. So what I'm going to do is take the derivative and find the critical numbers. So the derivative is equal to 12 x squared minus 192x plus 576. I want to set that equal to 0. I'm going to factor out 12. So let me draw this line. So 12 times x squared minus 16x plus 48, if you just pull out that, is equal to 0. And then if I factor this, I can get this to be 12 times x minus 4 times x minus 12 is equal to 0. So my critical numbers are 4 and 12. That's where I hit a 0. Now 12, again, it's just not feasible. If I cut 12-inch squares out of each side, there is literally nothing to fold up. Like, just there's nothing, right? It would be as though I cut on this piece of paper, I would have cut all of this. So there's nothing that can fold anymore. So that's a no-go. So 4 is the number that must make sense. So there it is. And we can use the first or second derivative test to clarify or to verify. I'll use the second derivative test. So the second derivative of this function, so here's my original function, right? The second derivative is equal to 24x minus 192. So if I plug a 4 in here, the second derivative, I know it's hard to see this, the second derivative of 4 is less than 0. It's negative, which confirms that this is a maximum. So when I go back to my original question, dimensions you should cut out 4-inch by 4-inch squares in order to maximize your volume. So I know this one's a lot messier on the board, but there's only one homework problem like it. It's really exactly the same different number. So go through the same process, try it on your own to make sure you're comfortable with it. The key here that I wanted you to see is that you end up with a primary equation that does not require a secondary because you have only one variable in it. So that's the important thing here. Okay. The third one was a practice one with perimeter and area. This is like one of those fancy ones. So there's a couple of homework problems that ask you to maximize or minimize perimeters or areas or fencing. So this one is a farmer, and it did come with a picture. This is number 3. I don't think I put the picture on the Word doc, but there's like a river where I wrote river, there's water. And they're fencing pasture land up against the river. So they have cows I think is what it was, cattle. Whatever it is, the animals aren't going to cross the river. So you don't need fencing along the river. You're going to have fencing on these three sides. And the farmer, so this is the given, the farmer knows he or she needs an area of 245,000 square meters in order, like that's how much grass that these cattle need to graze for a certain period of time. So this is the area that must be enclosed in order for the cattle to have the sufficient food and like for the grass to keep regrowing, etc., etc. So this is something they really think about. And this farmer wants to minimize the perimeter because you pay for it. If you're building a fence, you're paying for every foot of fencing, right? So they want to minimize the perimeter, and the perimeter is only going to have three sides because the riverside does not need fencing. And so the question is, what are the dimensions? So we want to find the dimensions. They're going to keep it rectangular shaped. So the dimensions of the rectangle that they fence in. Okay, so I'm going to call this X and Y. So our primary equation is the thing we want to maximize or minimize. In this case, it's the perimeter. We want to minimize the perimeter. So I'm going to say P is equal to X plus 2Y. There are not four sides, just three sides to this particular rectangle. And this has two variables, so I definitely need a secondary equation. So the secondary equation relates my two variables. So I know that the area is 245,000 meters squared, and that would be equal to X times Y. And then feasible domain. Well, I mean, again, you're not going to have a negative length, so it's got to be something between 0 and, I mean, clearly it's going to be much less than 245,000. This was kind of how I was thinking. I get a little sloppy with my feasible domain. Okay, so I write my primary equation. Primary equation is equal to X plus 2Y. And then I take my secondary equation, 245,000, which is equal to X times Y. I'm going to solve for one of the unknowns in the secondary equation and plug it into my primary. So I solve for X. So X is equal to 245,000 divided by Y. And I'm going to put that in here. So I say P is equal to X. I'll write that as 245,000 times Y to the negative 1. It's just a little easier for me to differentiate when I see it that way instead of divided by Y, plus 2Y. And I'm going to take the derivative of that. So derivative is equal to negative 245,000 times Y to the negative 2 power, or over Y squared. It's the same thing. Plus the derivative of 2Y, which is 2. And I want to set that equal to 0. So 0 is equal to negative 245,000 over Y squared plus 2. I'm running out of space on the board, but I'm just going to solve for Y here. So I'm going to add this term to both sides, do some dividing. And so I end up with Y is equal to 350 if I solve this. So we can use the first derivative test or the second derivative test to verify that this will give me a minimum perimeter. I'll do the first derivative test because I think I just did the second derivative test twice. So I'm going to make an interval out of this. I'll go from 0 to Y to 350, and then 350 to Y. You can go all the way up to infinity or to your domain value, or out of space, whatever. So I'm going to take a test value of 1 here, and I'll put in 400 here. Okay, so when I put 1 into my first derivative, the first derivative at 1 is, I've got to flip my page, I think it's negative to verify. It is indeed, so it's less than 0. And the first derivative at 400 excuse me, is greater than 0, which verifies that this is a minimum, and I was trying to minimize that perimeter. So if I'm trying to find my dimensions, Y is equal to 350, then I can go solve for X just using the area, and X is equal to 700. And that's it. again, here, the point of doing this one is really just to be careful with what is that primary equation versus secondary. So a lot of times we see area as our primary and then perimeter is secondary, because a lot of times we're trying to maximize or minimize area. But in this one, it's the perimeter we want to minimize because our cost is coming directly from the perimeter. So again, the thing that you want to maximize or minimize is always, always, always your primary equation, and then whatever else is given can be used to build a secondary if needed. All right,